Good evening, and welcome to Dream Theatre for a relaxed mind. Lay back, turn out the lights, and put on the kettle. Coffee, tea, or perhaps something even more ambitious. Tea and Gravity, a little corner of the universe where we let science take off its lab coat, put on its fluffiest dressing gown, and make itself a warm cup of something soothing. I'm Professor Teabottom, former astrophysicist, current biscuit philosopher, and tonight you and I shall journey into the delightful and surprisingly dramatic story of tides, the ocean's own bedtime story, whispered to it by the moon. Before we tumble headlong into tonight's sleepy tale of science and softly simmering wonder, a small request from your ever-thirsty host. If you find yourself enjoying these curious bedtime ramblings, do please like this video and subscribe to the channel. You see, the cost of decent tea these days is climbing faster than a startled electron, and if you've a moment more, consider joining our free Substack. There you'll be notified the moment a new episode appears, and you'll gain entry to a rather cosy salon of discussion, where we share thoughts, swap ideas for future episodes, and occasionally argue politely about whether gravity has a favourite biscuit. The link's tucked in the description like a note under a teacup. Now then, let's begin. If you've ever built a sandcastle, perhaps as a child or as an adult pretending to assist a child, you will know the creeping dread that accompanies the sight of water inching closer. You check the moat, you add a little tower, the tide continues to advance, you place a line of shells like a protective charm, the tide yawns, stretches and swallows the whole thing as if it had been invited, and you wonder, why? Why, dear moon, must you destroy what I so lovingly sculpted with this plastic bucket? Ah, but that is the story, isn't it? Before we dive too deep, and do mind your ankles, I invite you to get comfortable. Not just slightly reclined on the sofa comfortable, but wrapped in a blanket while a sleepy cat weighs down your legs. Kind of comfortable. We're going to take our time. The ocean doesn't rush after all, neither should we. I live in a modest stone cottage on the coast of Norfolk, where the gulls are slightly rude and the tides arrive as reliably as the post, though considerably wetter. From my study window, I can see the shoreline change its shape hour by hour, like a giant celestial creature breathing in and out. It was here, many years ago, watching the tide erase a rather elaborate sculpture I had made of Sir Isaac Newton, using nothing but driftwood and ambition, that I first truly appreciated the moon's influence on our world. The moon, you see, is not just a passive orb hanging above us for poetic inspiration and werewolf mythology. It's actively involved in shaping the world beneath our feet. Quietly, persistently, it's moving entire oceans, not through magic or whim, but through the oldest force in the book, gravity. We shall talk about that gravity, of course, in due course, and about Newton and tides, and even about my long-standing irritation with Bertrand Russell's biscuitless teapot metaphor. But we shall do so gently, softly, with the same kind of rhythm the sea follows as it slips back and forth across the sand. This episode, our very first, is called The Moon's Gentle Tug, Why Your Sandcastle Never Had a Chance. And by the end of our time together, you may find that you don't mind the loss of your little castle quite so much, that perhaps it was part of a larger, older and frankly more impressive dance, choreographed by cosmic forces that, for the most part, couldn't care less about your beach day. But first, let's admire the moon, let's properly meet her, and then let us drift, slowly, warmly, sleepily, into her embrace. Now then, are you tucked in? Has your tea cooled just enough not to scald the roof of your mouth? Good. Let us begin with a bit of moonlight and a lot of imagination. What is a tide? Not metaphorically, though the tide of history and the tide of public opinion are both lovely turns of phrase, but the actual, physical, wet and slippery tide that moves with eerie regularity along the edges of our continents. A tide, at its core, is the periodic rise and fall of sea levels caused by the combined effects of the gravitational forces exerted by the moon, the sun, and the rotation of the earth. But if that sounds a bit too much like a sentence from a textbook you once drooled on during a particularly uninspiring geography lesson, allow me to reframe. A tide is the ocean breathing, in and out, not with lungs, of course, though the idea of the Pacific sighing might be a rather good bedtime notion, but in a rhythm just as regular and in its own way, just as life-giving. Twice a day, more or less, The sea pulls back from the land as though deep in thought and then rolls in again, as if to share something important. These movements, high tide and low tide, don't happen everywhere at exactly the same time or with the same intensity, but they do happen. Relentlessly, predictably, comfortingly. The primary culprit behind this is, of course, the moon. Not content to simply light our romantic walks and inspire dreadful poetry, the moon also exerts a gravitational pull on the Earth. And our watery bits, being easily persuaded, respond with enthusiasm. When the moon is overhead, or more precisely when your particular patch of the Earth is facing the moon, the ocean is pulled toward it, creating a bulge of water. This is high tide. But wait, there's more. There is a second bulge on the opposite side of the Earth. You see, while the moon pulls the ocean on the near side toward it, the Earth itself gets pulled a tiny bit too, ever so slightly away from the water on the far side. That water, now relatively less tethered, forms another bulge, so we get two high tides, and in between them, two low tides. One bulge chasing the moon, the other flung behind like an afterthought or an elegant cape. The Earth spins beneath these bulges like a rotisserie chicken under a gravitational heat lamp, and each coastal area passes through the high and low tides in turn. The result is a steady cycle that has been with us long before we noticed, long before we measured, long before I dropped my first sandwich to an incoming tide. Now the sun plays a role too, which we'll get to in a future part. The sun's gravity also tugs at the Earth's oceans, sometimes working with the moon to create especially dramatic tides, called spring tides, and sometimes working against the moon to create particularly modest ones, called neap tides. But the moon is the star of this story, or perhaps the moon of it. Either way, she's the one who orchestrates the daily aquatic shuffle. It's easy to forget the sheer scale of it. These aren't puddles moving about. These are entire oceans shifting their weight in response to a gravitational nudge from a rock in the sky. Entire coastlines reshaped, harbours filled and emptied, sea creatures guided in and out, every day, without fail. There's something deeply reassuring about that. In a world of uncertainty, the tide will come in, and it will go out, and then it will do it all over again, with no need for reminders, alarms, or strongly worded memos. I once tried to time the tide with a series of antique clocks and a misbehaving parrot. It did not go well, but the tide came in nonetheless, indifferent to my efforts, just as it always has. Next, we'll meet the moon herself, the great orchestrator of watery rhythms and, incidentally, the best unintentional saboteur of seaside picnics. Now, it would be terribly rude of us to continue discussing tides without properly introducing the moon. We've been tossing her name about like a mutual friend at a dinner party, when really she's the guest of honour in our story, deserving of a little spotlight and possibly a biscuit. The moon is Earth's only natural satellite, though that makes her sound far less charming than she is. She's roughly 3,474 kilometres in diameter, about a quarter the size of Earth, and orbits us at a comfortable distance of 384,400 kilometres. Comfortable for us, that is. For the moon, I imagine it's like being tethered to an overactive toddler. She has no atmosphere to speak of, which is why her surface is so terribly pockmarked from all those uninvited meteorite guests over the eons. And she always shows us the same face, tidally locked, like a poker player refusing to reveal her cards. But that still unblinking face has held our fascination, since long before history had a decent stationery supply. Humans have sung to her, danced under her, blamed her for madness, and named her phases with poetic flair: waxing, waning, crescent, gibbous. A word, I must say, that sounds more like a particularly stubborn biscuit than a lunar phase. Would you like a chocolate gibbous with your tea? Oh no, they crumble too easily. But let's return to our scientific slumber. The moon's gravitational pull is the central player in the tide story. She exerts a force on the Earth, and this force affects everything, but most dramatically, the oceans. The gravitational pull isn't uniform. The side of the Earth closest to the moon feels a stronger pull than the centre of the Earth, and the centre feels more than the far side. This difference in pull creates a stretching effect, as if the Earth were made of particularly thick marmalade. It's important to note here that gravity isn't a magical rope tugging the ocean skyward. It's more like an invisible handshake between masses. The moon gently tugs, the Earth responds with a nod, and the oceans rise in polite agreement. No need for shouting or fanfare. Our ancestors noticed these patterns long before they understood the cause. The moon's position in the sky seemed linked to the sea's behaviour. Fisherfolk and sailors in ancient China, Greece and the Middle East all made careful notes. The Polynesians used the moon and stars to guide their incredible open-sea voyages, and the Babylonians tracked lunar cycles with impressive accuracy, though they sadly lacked the benefit of proper charts or waterproof trousers. There's something elegantly humbling about this, that for millennia humans looked up at the moon and felt its quiet influence on their lives, not with telescopes or satellites, but with intuition and attention. They didn't need to understand Newton's laws to know that the moon mattered. I once tried to host a lunar appreciation evening at my home. I provided telescopes, a variety of moon-themed snacks, and a brief lecture on tidal resonance. Unfortunately, the clouds had other ideas, and most of the guests ended up inside discussing biscuits instead. Still, I like to think the moon appreciated the gesture. We live in an era now where we can bounce lasers off the moon to measure its distance, send rovers to study its dust, and write very specific poems about its gravitational effects. But the moon herself hasn't changed. She still pulls the oceans, still steals the occasional sock from beachgoers, and still appears, night after night, ready to tell her part of the story. Next, we'll peer into gravity itself, the oldest mystery of them all, and try to understand why the moon's gentle tug has such an outsized effect on our watery world. Gravity, the universe's most persistent hug. Let us now tiptoe, ever so gently, into the arms of gravity, a force so familiar we often forget it's even there, like a polite ghost or a very dependable butler. Gravity is the force that attracts two bodies toward one another. It's why apples fall, why moons orbit planets, and why I once lost a rather expensive hat off a windy cliff. But unlike the more dramatic forces in the universe, electromagnetism for instance, which tends to shout, gravity is the quiet one, the steady one, the one that never misses a meeting. Sir Isaac Newton, who quite famously connected the dots between the apple and the earth, described gravity as a universal attraction between masses. Every object pulls on every other object. You are right now exerting a gravitational pull on your teacup. The teacup returns the favour. Neither of you is particularly good at it, but the effort is appreciated. The strength of this pull depends on two things: mass and distance. The more massive the object, the stronger its pull. The closer it is, the stronger its pull. This is why the Earth, being quite rotund, holds you firmly to its surface, while the Moon, being more modest in mass, affects only the things not nailed down, namely the oceans. Now, when the Moon pulls on the Earth's oceans, the water doesn't simply leap toward the sky like a startled cat. It bulges, slowly, broadly, with the kind of grace one might associate with a slumbering elephant shifting its weight. This is the high tide, and because of the Earth's rotation and a bit of gravitational cleverness we'll get into shortly, there are actually two bulges, one facing the Moon and one directly opposite. The water is pulled by the Moon on one side, and on the far side it's more that the Earth is pulled away from the water. The result? Two humps of sea travelling around the planet in sync with the Moon's gentle tug. These bulges move as the Earth rotates beneath them. This is what gives us the tide cycles, roughly 2 high tides and 2 low tides each day. The key word here being roughly, as the real ocean prefers jazz rhythms to classical precision. It's not just oceans that feel gravity's hug. The solid Earth also moves, albeit only slightly, under the Moon's pull. These are called Earth tides, and while they're usually only detectable by sensitive instruments or particularly fussy geologists, they serve as a reminder that even the seemingly immovable can be coaxed into a gentle sway by gravity's charm. There's something poetic about that. Gravity doesn't push, it doesn't shout, it simply attracts, always, tirelessly, without exception or complaint. The Moon pulls the ocean follows, and we, tiny tea-drinking inhabitants clinging to the surface, build our lives around the ebb and flow. When Einstein came along, he described gravity not as a force, but as a warping of space-time. Mass bends the very fabric of the universe, and other objects follow those curves. It's a bit like rolling a marble across a trampoline toward a bowling ball in the middle, though in my case the experiment ended with a cat and a very bruised sherry decanter. But whether you prefer Newton's tidy equations or Einstein's curvaceous cosmos, the effect is the same. Gravity keeps everything in motion, from tides to planets to wayward socks on laundry day. So the next time you feel the weight of the world, take comfort in the knowledge that it's not personal. It's just gravity, doing its job with the dedication of a librarian in a storm. Next, we'll explore those odd bulges in the ocean in a bit more detail and discover why the Earth is, in a very real sense, squishier than you'd expect. Tidal bulges and the squishy Earth. Now that we've spent some quality time with gravity, let us turn to one of its more curious manifestations, the tidal bulge. If you're imagining a celestial pillow puffing up beneath the moon's loving gaze, you're not entirely wrong. Though bulge may not be the most elegant term, it does the job. My wife describes me in a similar way to her mates. You see, when the moon pulls on the Earth's oceans, the water responds not with waves or splashes, but with a grand and stately swell, a great heaving bulge on the side of the planet facing the moon. This is the ocean lifting itself, not in rebellion but in tribute. Imagine a very slow curtsy made of water. But that's only half the story, because as we discussed, there's a second bulge on the opposite side of the planet. That one's caused not by the moon pulling directly on the water, but rather on the Earth itself, pulling it away from the water on the far side like a waiter removing a tray from beneath a slightly sleepy trifle. And so we get two high tides, one on each side of the globe with low tides in between. This arrangement circles the planet in lockstep with the moon's orbit, creating that twice-daily cycle of rise and fall we call the tide. And here's where it gets interesting. The Earth is not a perfect sphere, nor is it a rigid one. It's a bit squishy. Not custard squishy, but certainly more pliable than one might expect from something made largely of rock. This squishiness is technically called elastic deformation, and it means that the solid Earth also forms bulges, albeit much smaller, in response to the moon's gravitational pull. These Earth tides, yes, the land tides, are typically only a few centimetres in height, but they're measurable and quite real. Your living room floor, for instance, is rising and falling ever so slightly as the moon passes overhead. This makes tea balancing an underrated skill among astronomers. But the ocean, being less constrained, bulges more dramatically. The water piles up and then, as the Earth rotates, those bulges slide along the globe. If you're standing on the shore, it feels like the tide is coming in, when really, you're rotating under a bulge that was already there. It's rather like walking into a particularly wet hug. What's fascinating is how this movement isn't instantaneous. Water has inertia. It resists change, like a teenager confronted with a vacuum cleaner. So the ocean bulge lags slightly behind the exact position of the moon. It's pulled forward a bit by the Earth's rotation, and this lag means the moon's gravity doesn't pull directly downward, but slightly off-centre. And here lies a delicious twist. This off-centre pull actually transfers energy. The moon pulls on the bulge, and the bulge pulls back, and this mutual tug causes the moon to slowly drift away from the Earth by about 3.8 centimetres per year. It's not fast enough to cancel any holidays, but it's measurable. We've confirmed it with laser beams bounced off retro-reflectors left by the Apollo missions, which is possibly the most charmingly nerdy sentence in the English language. The result of all this is that the Earth's rotation is slowing down, ever so slightly. A day is getting longer by about 1.7 milliseconds per century. That means your great-great-great-grandchildren may enjoy slightly longer lie-ins, assuming society still values breakfast. All this from a bulge, a cosmic nudge, a gravitational whisper that travels through land and sea and time. I remember once trying to explain this at a village fete. I brought along a rotating globe, a bowl of water, and a particularly heavy grapefruit to represent the moon. It was going splendidly until a child asked quite seriously why the moon didn't just ask the ocean to move more politely. A fair question, I thought, and not one easily answered by Newtonian mechanics. Next, we'll examine how the sun gets involved, because of course it does. The sun is rarely one to sit out a gravitational gathering. Just when you thought the moon had the tide thing all to herself, along comes the sun. Like an older sibling with strong opinions and impeccable timing, the sun insists on joining the celestial choreography, and when the sun gets involved, things always become a bit more dramatic. The sun's gravitational pull on the Earth is about 178 times stronger than the moon's. Shocking, isn't it? You'd think that would make the sun the primary director of tidal affairs. But because the sun is also much farther away, about 150 million kilometres, give or take a missed exit, its tidal influence is actually less than half that of the moon. Still, it matters, and when the sun and moon align, pulling together like two particularly stubborn ants at opposite ends of a sofa cushion, their combined gravitational forces create what we call spring tides. These are not, as one might imagine, tides filled with extra bounce or floral optimism. No, spring in this case comes from the Old English to springen, meaning to jump or rise. And rise they do. Higher high tides, lower low tides, everything stretched to its extremes. Spring tides occur during the new moon and full moon phases, when the sun, moon and earth are in a lovely straight line, or nearly so. The oceans, feeling the tug from both sides, comply with a sort of resigned enthusiasm. It's like being called simultaneously by two parents who both think they're in charge of bedtime. The gravitational pulls partially cancel each other out, and the result is a modest tide. A no thank you, I'm full sort of tide. One that won't knock over your sandcastle unless it's particularly wobbly or insufferably proud. What's marvellous is how predictable it all is. We can calculate these tidal patterns centuries in advance, using only the positions of celestial bodies and some mathematics that would make your average biscuit tin sweat. It's celestial clockwork, with the ocean as its pendulum. I once tried to explain the concept of spring and neap tides using a tea tray, a bowl of water, and two cats named Archimedes and Gravy. It was going brilliantly until Gravy decided the moon's role could be improved by pouring the bowl onto the carpet. The demonstration ended in chaos, but I like to think the point was made. These lunar and solar interactions don't just affect seaside strolls, they influence navigation, fishing, and even the behaviour of certain species. Coral, for instance, times its mass-spawning events with the tides, ensuring the best possible chance for its offspring to find a suitable bit of reef, and not, say, a snorkeler's armpit. The interplay of moon and sun isn't just a gravitational tug-of-war, it's a partnership, occasionally competitive, occasionally collaborative, always influential. Together, they shape the rhythms of our world in ways we've relied on for millennia, long before anyone thought to write it down or to narrate it with a biscuit in hand. Next, we'll step back to the shore and see how this cosmic tugging plays out where land and sea meet. Tidal flats, mud flats, and the unfortunate business of losing one's left shoe in particularly sticky sand. Coastal theatre, high tide, low tide. Let's now bring our story back to Earth, specifically to the line where Earth and ocean meet in their daily dance, the coast. If the moon and sun are the playwrights of the tidal tale, the coastline is the stage complete with dramatic entrances, vanishing acts, and the occasional soggy audience member. At its most basic, the coast is where the sea stops being entirely sea, and the land starts being suspiciously damp, but it is here that the effect of tides becomes truly visible. Twice a day, the ocean arrives like a punctual guest, sweeping in to reclaim its territory. And then, as if it remembered it left the kettle on, it slips away again. High tide and low tide aren't merely labels on a chart, they're moving, breathing events. High tide is the point when the ocean has advanced as far as it will go, swelling against the land, filling inlets and harbours, wrapping round piers and nudging the toes of those who misjudge the timing. Low tide, by contrast, is when the ocean has retreated, leaving behind tide pools, glistening sand and, if you're lucky, bits of pirate treasure, or if you're less lucky, someone's lost flip-flop. Not all coasts experience tides the same way. Geography matters. In some places, like the Bay of Fundy in Canada, the tide difference is extreme, up to 16 metres. In other locations, the variation is so slight you might miss it if you blink, or if you're distracted by a sandwich, which I often am. The shape of the coastline, the depth of the water, the position of underwater ridges and basins, all of these influence the local character of tides. It's not unlike how the same piece of music sounds different depending on who's playing it. Some coasts perform a dramatic overture, others prefer a gentle lullaby. I once spent a week at a tidal estuary sketching the shifting waterline. I was determined to record the exact boundary of the tide using only charcoal, patience, and an unusually cooperative seagull. The result was a series of increasingly soggy sketchbooks and one rather memorable sunburn. But the exercise taught me something important. The tide doesn't just rise and fall. It moves sideways, creeps upward, retreats in curls and ribbons. It behaves less like a machine and more like a mood. Tidal flats, those broad, muddy expanses that emerge at low tide, are rich ecosystems, teeming with life and the faint smell of damp socks. They may look barren at first, but a closer inspection reveals armies of crabs, plodding snails, darting fish, and the occasional bird who appears to be running late for a very important puddle. These areas are also treacherous for the unwary. Wet sand can become a trap, and the tide returns faster than most people expect. There's an old saying, "The tide waits for no man," which is entirely true, unless the man is carrying chips, in which case seagulls may delay proceedings. Communities built near the sea have long shaped their lives around the tides. Fishing schedules, ferry crossings, even the opening hours of some seaside ice cream parlours all bow to the rhythm of the water. In medieval Europe, monks in coastal monasteries would schedule prayers to coincide with the turning of the tide, which gives a whole new meaning to divine timing. And let us not forget the poetry of it. The sea coming in and out, like breath, like thought, a pause, a return. There's comfort in its constancy, even as its timing shifts from day to day. You can plan around the tides, but only if you listen first. Next, we'll talk about time itself, and how the moon, the tides, and ancient sky watchers work together to shape the very way we measure our days. A lunar day is not what you think. If you've been assuming that a day, any day, is simply 24 hours long, evenly divided between yawns, cups of tea, and occasional productivity, you'd be mostly correct. Unless, of course, you're the moon. Then things become delightfully peculiar. The moon, you see, doesn't orbit the Earth as a pet might circle its owner in a burst of enthusiasm. No, it ambles, with deliberate dignity. And because it's tidally locked, showing us only one face as it travels around us, it's always halfway turned toward Earth, like a bashful actor who's memorized just one flattering angle. Now, here's the twist. The moon takes about 27.3 Earth days to complete one orbit around us. But from our perspective on Earth, thanks to our own movement around the sun, a full lunar day, from one moonrise to the next, actually lasts closer to 29.5 days. That's longer than a February with commitment issues. And what does this have to do with tides? Quite a lot, as it turns out, because the tide cycle, the high and low of it, is influenced not only by the moon's position, but by its apparent motion across our sky. As the Earth rotates, we pass beneath the tidal bulges caused by the moon, but because the moon is moving in the same direction as Earth's rotation, we take just a bit longer than 12 hours to go from one high tide to the next. On average, the interval between two high tides is about 12 hours and 25 minutes. This means that each day the high tide occurs roughly 50 minutes later than the previous day. If you ever wondered why your beach picnic got soaked on Tuesday but not on Monday at the same hour, blame the moon's leisurely pace. I once tried to coordinate a seaside tea party with a tide schedule, only to have the table vanish mid-scone. The guests were polite about it, British to the last, but the clotted cream was never seen again. This 12-hour 25-minute rhythm creates what's called a semi-diurnal tide, 2 high tides and 2 low tides each lunar day. But not all places experience this. Some regions see just 1 high and 1 low tide each day, diurnal tides, while others have mixed tides with unequal highs and lows. It's as if the ocean occasionally forgets its lines and improvises with jazz hands. These variations depend on coastal shape, seafloor topography, and the moon's specific position relative to both Earth and Sun. It's a bit like a recipe that changes slightly depending on altitude, humidity, and whether the chef is in a good mood. Understanding the lunar day and how the moon's stately progress causes daily tidal timing to shift is crucial, not just for poetry and science, but for anyone who's ever tried to moor a boat, gather mussels, or chase a particularly evasive beach ball. It also explains why the tide chart you tacked to your fridge has so many numbers. Those tables are not just for show, they are the work of meticulous lunar math and dedicated oceanographers, many of whom have strong opinions about waterproof ink. So the next time you look up at the moon, give her a little nod of respect. She's taking her time, yes, but with good reason. She's guiding the oceans, setting a rhythm older than civilization itself, and all we need to do is listen, and perhaps not leave our biscuits too close to the shoreline. Next, we'll take a historical stroll and meet the ancient observers who first noted these patterns, long before tide charts, clocks, or indoor plumbing. Ancient tidal watchers. Long before telescopes, tide charts, and helpful apps that beep when your wellies are about to get wet, humans were already watching the sea. They noticed that the water came in and went out, not randomly, but with a sort of rhythm, as though the sea were keeping time to a music only it could hear. These early observers were not scientists in the modern sense. They were fishermen, sailors, farmers, priests, people who lived close enough to the coast to have their plans ruined by a poorly timed high tide. And so they did what clever humans always do when faced with a mystery. They watched, they noted, and eventually they predicted. In Mesopotamia, over 4,000 years ago, the Babylonians tracked the movement of the moon and correlated it with changes in the river levels. They didn't have the concept of gravitational pull, but they knew something was up, literally. The moon waxed, waned, and the waters followed suit. The ancient Greeks, always keen on writing things down and taking credit for them, began to formalize these observations. The philosopher Pytheas of Massalia, around 300 BCE, was one of the first to explicitly link the moon with the tides. He noticed that high tide tended to occur when the moon was overhead, or when it was nowhere to be seen, lurking on the far side of the earth. His writings were lost to time, but his idea floated on. In India, texts dating back to the 6th century mention tides and even attempt early predictions. The Tamil poem Purananuru makes note of the sea's movement and its impact on daily life. In China, the great polymath Shen Kuo wrote in the 11th century about the moon's influence on water, noting that tidal strength varied with lunar phases. Meanwhile, in the Pacific, the Polynesians, navigators of legendary skill, used tidal patterns along with the stars and ocean swells to journey between islands thousands of miles apart. Their understanding wasn't written in scrolls, but passed down through oral tradition, chants, and the orientation of woven mats and canoe shadows. It's a humbling thing, isn't it? That across continents and cultures, humans figured out that the moon had something to do with the sea. They lacked Newton's equations or satellite data, but they had patience, keen eyes, and a vested interest in not being surprised by the incoming tide while collecting oysters. I once attempted to recreate an ancient tidal calendar, using only a stick, a coconut shell, and a flock of increasingly uncooperative ducks. I won't say the experiment was a complete failure, but I will say the ducks have formed a union. These early tide watchers didn't just observe for fun, their livelihoods depended on it. Knowing when the tide would turn meant safer harbours, more productive fishing, better timing for salt harvesting or seaweed gathering. Tidal knowledge wasn't academic, it was survival. The moon was often treated with reverence, even worship. She was not just a rock in the sky, she was a deity, a guardian, a celestial clock ticking through an invisible cycle. Her phases became metaphors for life itself, birth, fullness, decline and renewal, and tides following her became a kind of language, one that people learned to read long before they learned to write. Next we'll look at how modern minds, from Galileo to Newton to Laplace, turned these ancient hunches into the science of tides we know today. There will be math, yes, but also drama, jealousy, and a particularly ill-fated barrel of apples. If our last chapter was a gentle wade through the observations of ancient tide watchers, this one is more of a cannonball into the pool of Enlightenment science. Prepare your towel and your wig, because the great minds of Europe are about to enter the scene, some more gracefully than others. We begin with Galileo Galilei, a man who once built a telescope, looked up, and profoundly irritated the church. Galileo was many things: astronomer, physicist, mathematician, occasional grumbler. But when it came to tides, even he got it wrong. Galileo believed that tides were caused by the rotation of the Earth and its motion around the Sun. He thought the sloshing of the oceans was like water in a moving basin, accelerating and decelerating as the Earth wobbled along. In a letter from 1616, he confidently declared that this was the only cause of tides, and anyone who disagreed was engaging in vain philosophy. Unfortunately for Galileo, the moon did not read his letters. His theory didn't match the observations. It couldn't explain the timing of tides, or the fact that they occurred twice a day in most places. But he was so determined to dismiss occult explanations, like unseen forces or celestial pull, that he refused to consider lunar gravity. In short, brilliant man, spectacular beard, questionable tidal theory. Enter Sir Isaac Newton some decades later, with a head full of calculus and a suspiciously well-timed apple. Newton's genius was in realizing that gravity wasn't just something that kept your teacup on the table. It was a universal force. The moon pulled on the Earth, and here's the important bit, it pulled more strongly on the side of Earth closest to it. This explained the tidal bulges. It explained the 2 high tides per day. It explained why Galileo's bathtub idea was more bath than theory. Newton's Philosophia Naturalis Principia Mathematica, published in 1687, laid the groundwork for everything that followed. It was like turning on a light in a previously waterlogged room. But the story didn't stop there. In the 18th century, a French mathematician named Pierre-Simon Laplace took Newton's ideas and applied them to the real oceans, considering things like the shape of coastlines, the depth of water, and the speed of waves. Laplace developed a set of equations so complex they still frighten undergraduates to this day. His dynamical theory of tides accounted for not just gravity, but the Coriolis effect and resonance phenomena. He essentially wrote the musical score for the ocean's dance. I once tried to explain Laplace's tidal equations to a group of schoolchildren using a bowl of jelly and some very optimistic metaphors. The jelly was later confiscated for safety reasons. The leap from observation to theory was monumental. For centuries people had known what tides did. Now, at last, they knew why. The moon pulled, the earth responded, and the sun, with all its might, occasionally chimed in like an enthusiastic baritone. Tides became not just curiosities, but subjects of study. Mathematical models improved, and predictions became more accurate. In Britain, the first tide-predicting machines, enormous, gear-filled contraptions, were built in the 19th century. These weren't just gadgets. They were national assets, used to plan naval missions and avoid shipwrecks. We'll explore those machines a bit later, but for now, let's raise a teacup to Newton and Laplace, men who turned the moon's mysterious pull into a science, and perhaps a slightly less enthusiastic toast to Galileo, who, despite his many accomplishments, really ought to have looked up more often. Next, we'll dive into the role of tides in navigation and empire, the way they shaped exploration, commerce, and the occasional very wet battle plan. Tides and empire, when the sea dictated power. Let us now venture into the age of sails, spice routes, and slightly uncomfortable woolen uniforms, the age when nations jostled for power on the high seas, and the tides played a quiet, powerful hand in the game of empire. You see, before steam engines and GPS, maritime navigation relied not only on maps and stars, but on knowing the tide. When the ocean would rise, when it would fall, and how much of your hull was going to be scraping the seafloor, this wasn't just trivia, it was strategy. Let us begin in Britain, because frankly, it insisted. The British Empire, with its passion for charts, flags, and afternoon tea, was deeply invested in understanding the tides. The Royal Navy, whose ships set out to rule the waves, very much preferred those waves to be predictable. A well-timed tide could mean the difference between a swift entrance to a harbour and an embarrassing wait on a sandbar, waving at amused locals. In the 18th and 19th centuries, Britain began producing detailed tidal charts for its ports. Observers noted the highs and lows with the sort of dedication usually reserved for cricket scores or mysterious hedgerow disputes. These records became the backbone of naval logistics, shipping routes, and colonial infrastructure. The East India Company, for instance, timed many of its departures from London's docks with the ebbing tide of the Thames. The idea was simple. Let the river carry the ship gently out to sea, saving on manpower and avoiding the risk of looking foolish in front of dockside pigeons. Tides also played an essential role in exploration. Captain James Cook, that well-mapped man of maritime fame, paid close attention to tidal charts when navigating treacherous coastal waters. On more than one occasion, his survival depended on knowing exactly when the sea would lift his ship away from jagged coral or hungry rocks. Further afield, Dutch, Portuguese and French seafarers all relied on tide knowledge. In Southeast Asia and the Indian Ocean, mastery of the monsoon winds had to be coupled with an understanding of tidal windows. Miss the tide, and your lucrative cargo of cinnamon, pepper or decorative parrots might arrive 6 weeks late and smell faintly of mildew. Even land battles were shaped by tides. The Battle of the Somme during World War I was partly planned around tidal movements in the nearby rivers and estuaries. Napoleon himself misjudged the English Channel's tidal behaviour when dreaming of an invasion. The tides, it seems, were loyal to no emperor. Closer to the present day, the Allies used meticulous tidal calculations to time the D-Day landings in 1944. The planners needed low tide to reveal the German beach defences. but also needed enough daylight and rising water for the follow-up troops and supplies. That narrow window determined not just the hour of the assault, but its very success. There's something profound in that, isn't there? That the rise and fall of the ocean, a process billions of years old, became the clockwork by which empires expanded, battles were won, and tea arrived on time. I once attempted a reenactment of a historical naval manoeuvre in my bathtub using wind-up ships and a fan. The result was inconclusive, but the cat has since refused to enter the bathroom. So the next time you stand by the shore and watch the sea retreat, remember, you're standing on what was once a battlefield, a trading hub, a highway for empires, and all of it moved to the moon's quiet rhythm. Next, we'll turn to the Industrial Age and the creation of the first tide-predicting machines, gears, wheels, and a bit of Victorian bravado. The machines that predicted the sea. By the 19th century, humans had developed a curious and distinctly Victorian impulse, the desire to build enormous, whirring, clanking machines to solve problems that had previously been managed with observation, scribbled notes, and a healthy respect for soggy boots. Enter the tide-predicting machine. As the need for accurate tidal information grew, spurred by expanding empires, industrial shipping, and a general aversion to running aground, a number of very clever individuals set about creating devices that could model the tides mechanically. The first of these was conceived by Sir William Thomson, better known to the scientific world as Lord Kelvin. Yes, that Kelvin, the one who gave his name to the temperature scale that never quite reaches zero unless you've insulted a physicist. In 1872, Kelvin introduced a machine that could calculate future tides using a series of gears, pulleys, and rotating discs. It looked rather like the inside of a grand piano had gotten ideas above its station. The idea was simple, even if the execution wasn't. Tides can be represented as the sum of many different periodic components, sine waves of various lengths and amplitudes. These components are influenced by the moon, the sun, and other celestial mechanics. Kelvin's machine added all these sine waves together mechanically, producing a wiggly line on paper that represented the expected tide level at a given time and place. It was, in a word, brilliant. It was also deeply satisfying to watch. Soon, similar machines were built in Britain, the United States, France, and beyond. Some were compact, others took up entire rooms. The British government used tide-predicting machines for decades, especially at the Admiralty in London, where naval planners could walk in, wind a few cranks, and walk out with a perfectly scheduled invasion. Or, at the very least, a dry pair of socks. One such device, number 2 tide-predicting machine, built by Edward Roberts in 1912, remained in operation for over 50 years. It could predict tides for years in advance, and its accuracy was astonishing, especially considering it didn't have a microchip to its name. I had the great privilege of visiting one of these machines once, housed in a museum like a retired magician. There it stood, all brass and polish, humming softly as it traced the future of the sea with a pen no thicker than a matchstick. It made me wonder if perhaps the sea could be charmed after all, with gears, levers, and just a touch of Victorian flair. Of course, these machines eventually gave way to electronic computers, which could perform the same calculations in a fraction of the time, without needing to be oiled or spoken to gently. But there's a romance to the old models, a sense that we once tried to capture the ocean's secrets with cogs and string. And let's not forget the human side of it. These machines were built by people who loved the sea. Not just its beauty, but its math. They spent years perfecting the mechanisms, tuning them like instruments, listening for the music of the tide. So next time you check a tide chart on your phone, spare a thought for the engineers in waistcoats and spectacles, hunched over blueprints, dreaming of clockwork oceans. Next, we'll look at the creatures who follow the tides. Not sailors or scientists, but the animals whose very lives are tuned to the moon's watery lullaby. Part 13. Moonlit Marches. Creatures that follow the tide. Let us now turn our gaze from equations and empire to the soft-footed, gilled and tentacled residents of our planet. Creatures who live and die by the rhythm of the tides. While we humans often treat the ocean as a place to paddle or occasionally misplace our sunglasses, these animals treat it as a calendar, a clock and a calling. First among them are the crabs, notably the fiddler crab, whose lifestyle is dictated by the tides with a precision that would make a train conductor weep. Fiddler crabs scuttle across mudflats when the tide retreats, searching for food and love, though not necessarily in that order. They build burrows just above the high tide line, popping in and out with impeccable timing. If the moon were to ever call in sick, these crabs would be utterly flummoxed. Then there are grunion, small silvery fish found on the beaches of Southern California. During the spring and summer months, under the cover of high tides and moonlight, grunion come ashore en masse to spawn. They flip and flop on the sand in a bizarre shimmering ballet, lay their eggs, and then return to the sea before the tide betrays them to seagulls and scandal. The eggs, quite sensibly, remain buried in the sand, waiting for the next series of high tides to wash them out and hatch them. It's one of nature's great timed release schemes, and it works with eerie accuracy. I once attempted to witness this event myself, armed with a flashlight, a thermos of tea, and a questionable sense of direction. I found no fish, but I did startle several confused joggers, and one rather judgmental raccoon. Moving further afield, we find the horseshoe crab, a living fossil that predates most forms of modern tax collection. Every year they gather in huge numbers along the eastern coasts of North America, using the spring tides around the full and new moons to lay their eggs in the sand. These eggs, in turn, feed migratory birds on their long journeys, making the horseshoe crab not just a tidal traveller, but a crucial link in a much larger web. And let us not forget the coral. Yes, the stationary, stony, underwater architects of reefs. Many coral species engage in a mass spawning event once a year, synchronised with the lunar cycle. Millions of tiny eggs and sperm are released into the sea all at once, a shimmering underwater snowstorm of future reefs. It's biology's version of a lunar disco, and it's every bit as surreal as it sounds. What ties all these creatures together, apart from a healthy fear of seagulls, is their reliance on the moon. They have internal clocks, yes, but these clocks are set by external cues: the tide, the light of the moon, the pressure of water. Evolution, it seems, has handed them a timetable and said, "You may not be able to read this, but you'll feel it." This phenomenon is known as circulunar rhythm, and it's as real as your circadian rhythm, only it runs on a 29.5-day lunar cycle instead of 24 hours. Some fish, crabs, worms, and even birds use this rhythm to guide reproduction, feeding, and migration. Nature doesn't own a wristwatch, but it does keep excellent time. It's a poetic reminder that life on Earth hasn't just adapted to the land or the air. It's adapted to the pull of another world. The moon, distant and silent, reaches down through gravity and light to tell shrimp when to dance and coral when to flirt. Next, we'll look at how humans too are shaped by the moon, not just physically but mythically. From madness to menstruation, moonlit myths abound. Part 14, Ocean Resonance, When the Sea Sings Back. By now, we've accepted that the moon's pull causes the ocean to rise and fall, rather like a slow, watery breath. But sometimes, under just the right conditions, the ocean doesn't simply rise and fall. It resonates, it hums, it wobbles in tune, like a wine glass touched just so. And if that image makes you thirsty, feel free to pause for tea. Resonance is what happens when an external force matches a system's natural frequency, amplifying its motion. You've seen this with a swing. Push it at just the right time, and it goes higher and higher. Push it at the wrong moment, and you're just an awkward adult at a playground trying to explain physics to a toddler. In the case of oceans, the push comes from the gravitational tug of the moon, and to a lesser extent the sun, while the natural frequency is defined by the shape and depth of the ocean basin. If these two things align, the tide in that area becomes supercharged. The ocean enters a kind of gravitational duet. One of the most famous examples is the Bay of Fundy in eastern Canada. This peculiar bay is shaped in such a way that its natural oscillation period, about 12.4 hours, matches the frequency of the moon's tidal cycle. The result? Tides that can reach up to 16 metres, enough to hide small buildings or in some cases greatly distress unaware kayakers. It's like the moon has found the perfect note, and the Bay of Fundy sings back with gusto. This kind of tidal amplification is called a resonant tide or tidal resonance. It doesn't happen everywhere. It requires a certain geometry. Long, narrow bays, estuaries, and even enclosed seas like the North Sea or the Gulf of California can all experience forms of resonance, depending on their dimensions. I once attempted to build a model of the Bay of Fundy in my bathtub using only cereal boxes and a pair of stolen garden gnomes. While it was not scientifically rigorous, I can confirm that the smaller gnome survived the tidal resonance better than expected. Resonance can also explain why tides behave so oddly in certain harbours. In some places, water levels rise and fall sharply. In others, they might barely shift. And some, like the port of Southampton in England, have a famous double high tide due to overlapping wave reflections, sort of a marine echo chamber. It's the ocean's version of forgetting the lyrics and repeating the chorus. It's not just vertical motion either. Resonance can create powerful horizontal currents, funneling water in and out of bays with great force. Sailors, for obvious reasons, care deeply about this. So do fish, and ducks, and anyone trying to enjoy a sandwich near the shore. These dynamic tidal behaviours shape coastlines, influence ecosystems, and affect human activities from shipping to flood defence. They also make excellent metaphors for unexpected emotional outbursts, should one be inclined toward poetry. Understanding ocean resonance requires mathematics, yes, but it also demands imagination. The sea is not a passive receiver of gravitational influence. It responds, it echoes. It rings like a bell struck gently but insistently by the moon's invisible hand. Next, we'll travel to the far corners of the Earth to see how tides operate in the extremes, from the polar seas to the equator, and from hidden fjords to bustling tropical ports. Part 15. Tides at the edges, poles, tropics, and everything between. By now we've grown comfortably familiar with the rhythm of the tides, their rise and fall, their celestial choreography, but tides don't behave the same everywhere. In fact, depending on where you stand on this spinning, soggy marble we call home, the tide can behave like an overachiever, an introvert, or that one uncle who only shows up at weddings with a very loud laugh. Let's begin at the poles. In the Arctic and Antarctic, the icy margins of the Earth present unique tidal challenges. For one thing, sea ice complicates the show. It's like trying to watch a ballet through a layer of frosted glass. The tides are still there, of course. Gravity doesn't take tea breaks, but their effects are often hidden beneath the ice. Underneath those frozen lids, water still sloshes back and forth, pushing ice shelves and affecting ocean circulation in ways that are both subtle and significant. In some polar regions, tides also contribute to the slow chewing away of glaciers. When seawater rises during high tide, it seeps into crevasses at the ice's edge. When it falls again, it pulls at the glacier's face like a curtain tugged by a curious child. Over time, this wears away at the ice, hastening calving events, the dramatic break-offs of icebergs. And then we head toward the equator, where things are warmer, livelier, and often a bit more theatrical. Tropical tides behave differently, thanks in part to the Earth's equatorial bulge and the shape of the ocean basins. In many equatorial locations, tides are diurnal, meaning just one high and one low tide per day, instead of the more common semi-diurnal pattern. This often surprises tourists, who expect the tide to behave the same everywhere, and are left wondering why the water seems to be ignoring the moon's polite invitation. Island chains near the equator, such as the Maldives or Micronesia, also experience complicated tidal flows due to the interaction of local currents, wind, and the seafloor's shape. In some places, tides shift sideways instead of straight in and out, like a sideways elevator operated by an invisible octopus. Between these extremes lie the world's temperate zones, where tides are most easily observed and studied. These are the regions of tide pools, sandy beaches, and the sort of wooden piers that look picturesque right up until someone drops a mobile phone through the slats. What's remarkable is how much local geography influences tidal behaviour. A bay may have enormous tides, while the neighbouring coast sees barely a ripple. A fjord may amplify tides like a trumpet, while a wide open bay diffuses them like a sigh. Even inland seas like the Baltic can experience measurable tides, though they're often so subtle you'd need sensitive instruments or a very bored beachgoer to notice. I once tried mapping tidal variations across the globe with coloured pins and a large corkboard. It went quite well until a curious parrot relocated all the pins to what he insisted was a more sensible arrangement. His map had surprisingly good symmetry, though a troubling number of pins in the kettle. The key takeaway is that tides, while governed by universal forces, express themselves locally. They are both global and intimate, predictable in theory, surprising in practice, much like dinner parties or weather in Wales. Next, we'll turn our attention skyward, beyond the moon and sun, to explore how other celestial bodies influence our oceans ever so slightly, and how tidal forces might shape distant worlds. we've spent many chapters gently paddling through the moon's oceanic influence, with the sun occasionally stepping in like a well-dressed chaperone. But there are other members of our celestial neighbourhood, and while their gravitational pull on Earth is comparatively minor, they're not entirely without impact. Let's spare a moment for the bit players, the planets, asteroids, and various interstellar gatecrashers who occasionally add their 2 pence to the tides. First up, the planets. You might wonder if gas giants like Jupiter and Saturn, with their brooding bulk and magnetic swagger, ever give Earth's tides a bit of a nudge. The answer is yes, barely. Their gravitational effect is measurable, but only just. Jupiter's pull on our oceans is less than a 10,000th that of the Moon. That's roughly the equivalent of trying to stir your tea from across the room with a very determined look. Still, during planetary alignments, those rare moments when several planets line up on the same side of the Sun, there is a small cumulative effect. It doesn't produce dramatic tidal surges, mind you, but it does give oceanographers something to scribble about in the margins of their notebooks, and astrologers something to shout about on social media. More intriguing, perhaps, are the lunar perigees and apogees, the points in the Moon's elliptical orbit when it is closest or farthest from Earth. When the Moon is at perigee, closest, its gravitational pull is stronger, and the resulting tides, called perigean spring tides, are a bit more exaggerated. They're also sometimes referred to as king tides, which sounds wonderfully regal until you realise they mostly just make beachfront cafes slightly soggier. On occasion, the Moon also aligns with the Earth and Sun at its perigee, producing a supermoon, when it appears larger in the sky and does its best impression of an over-enthusiastic dinner guest. During these events, the tide swells slightly higher than usual, prompting both awe and, in some cases, a bit of overreaction from headline writers. Asteroids, meanwhile, don't do much. They're small, uncooperative, and rarely come close enough to matter, like certain cousins at family reunions. Still, on a cosmic timescale, a close flyby of a large object could theoretically produce a temporary tidal blip. And if an asteroid ever did strike the ocean, the resulting waves would be less tide and more please hold on to your eyebrows. But perhaps the most fascinating part of all this isn't how these distant bodies affect our tides. It's how tides might play out on other planets. Take Jupiter's moon Io, for instance. Its proximity to Jupiter's immense gravity causes tidal flexing, internal heating that keeps its volcanic activity constantly simmering. Or consider Europa, another Jovian moon whose subsurface ocean is kept liquid by tidal forces. Some scientists believe that life could exist there, hidden beneath the icy crust dancing to the rhythm of Jovian tides. It's poetic, really. The same forces that rock our oceans might also stir the hidden waters of alien worlds. I once attempted to simulate extraterrestrial tides in my kitchen, using a salad spinner, a small watermelon, and glitter. The results were inconclusive, but the glitter is still embedded in the ceiling. So yes, the moon remains our primary tide master. The sun provides a strong second fiddle. But elsewhere in the solar system, and perhaps beyond, tides play out their own versions of this gravitational waltz, quietly shaping worlds we've barely begun to understand. Next, we'll dive into the fascinating relationship between tides and timekeeping, how the ebb and flow helped us measure the immeasurable. The ocean as a clock. It may surprise you to learn that long before wristwatches, atomic clocks and mobile phones that beep at you for standing up incorrectly, humanity looked to the tides to help tell time. The ocean, in all its watery mystery, was once the world's clockmaker, and a rather punctual one at that. The ancient understanding of tidal regularity, especially in semi-diurnal regions, allowed people to predict when the sea would rise and fall. Fisherfolk, sailors, monks, and even farmers used these patterns to plan their days. And while the moon didn't wear a top hat and carry a pocket watch, as far as we know, it may as well have. Let us begin with the most obvious connection, the lunar day. As we've discussed, a lunar day is roughly 24 hours and 50 minutes. This is the time it takes for the moon to return to the same position overhead, and it's why tides shift forward by nearly an hour each day. It's also why, in coastal villages, tide time was sometimes more important than sun time. You might not know precisely when lunch was, but you knew exactly when the fish would bite. In medieval Europe, coastal abbeys and monasteries built their schedules around the tides. Some even rang bells not at noon, but at high tide. It created a rhythm of life that was beautifully synced to the sea and utterly confusing to visitors from inland. In the 17th and 18th centuries, as maritime travel expanded, the need for accurate timekeeping became acute. Knowing the precise time was essential for calculating longitude at sea, which in turn required the invention of accurate chronometers, essentially very stubborn clocks. But tide tables too were key. If you knew when the tide turned, you could estimate your position with some accuracy, even on a cloudy night when the stars played coy. Fast forward to the Victorian era, and we find tide clocks mounted in seaside towns. These cheerful devices pointed not to the hour but to the next high or low tide. Imagine checking the wall to see, not whether it's tea time, but whether your fishing boat might still be floating. Some of these clocks were charmingly optimistic and often wrong by a few minutes, but what they lacked in accuracy, they made up for in nautical charisma. Interestingly, some scholars argue that our earliest calendars were inspired by tides and lunar cycles. Coastal peoples may have first counted time by the coming and going of the sea, then formalised it into moons, months, and eventually calendars, presumably once they grew tired of writing Tuesday wet again. Even today, tide charts represent some of the most precise time forecasts we have. Oceanographers can predict tides years, decades even, into the future with remarkable accuracy, using equations first dreamed up by Newton, refined by Laplace, and ultimately verified by countless soggy notebooks. I once attempted to build a tide clock out of an old cuckoo mechanism and a siphon. It worked perfectly for 2 hours, after which it exploded and covered the cat in peppermint tea. The cat has not forgiven me. But the idea of time tied to the sea is a beautiful one, isn't it? Unlike mechanical clocks that tick regardless of the world outside, the tide measures time in motion, in rhythm, in relationship with celestial bodies. It reminds us that time isn't just something we invented to be late for meetings, it's something the universe does. Next, we'll dip into the cultural tides, myths, legends, and stories that ripple through the ages, inspired by the sea's constant coming and going. Myths of the tides, folklore from the floodline. Where there are tides, there are stories. And not just the ones involving misplaced picnic baskets. Human cultures around the world have gazed upon the sea's steady breathing and seen not merely physics, but poetry. Before the moon was a mass with gravitational influence, she was a goddess, a trickster, a grandmother, a clock made of silver and dreams. Let's wade into the myths. In Maori mythology, tides are explained by the tale of the sea god Tangaroa and his many children. The ebb and flow of the sea are said to be caused by their arguments and reunions. The details vary across different iwi tribes, but the theme is always one of motion, family, and the moodiness of divine aquatic beings. In West African folklore, particularly among the Yoruba, the goddess Yamoja is a spirit of the ocean, motherhood, and the moon. She controls the waves and brings both blessings and tempests. Sailors offer her gifts to calm the sea, often tossing trinkets into the surf, though I once tried this with a chocolate biscuit and the sea was unimpressed. Meanwhile, the Norse had the Midgard serpent, Jomungandr, a colossal sea serpent so large it encircled the world and grasped its own tail. When it shifted in the sea, great waves and tides were said to follow. Frankly, if I had to live in a cold sea wrapped around a globe, I might cause a few tsunamis myself. In Japan, the Shinto tradition speaks of the moon god Tsukuyomi and sea kami who influence the tides. The sacred ritual of misogi, a form of purification, is often done at tide pools or river mouths, symbolising a balance between the flowing and the fixed. Celtic lore from the British Isles often personified the sea as a capricious entity. In Cornish legend, the tide was governed by the sea giant who drank the sea down and belched it back twice daily. While scientifically suspect, it is emotionally relatable. Even the Bible makes tidal allusions, with the parting of the Red Sea often interpreted as a miraculous event, possibly timed with tidal ebb in a reed-rich estuary. And let's not forget King Canute, the famously humble monarch who sat on a throne at the shoreline to demonstrate that not even royal decree could halt the tide. A masterclass in managing expectations. Stories like these are more than curiosities. They represent early attempts to explain the inexplicable, to make sense of a force that was rhythmic, reliable, and yet utterly beyond control. When you're a coastal villager without access to Newton's Principia, attributing the tides to a moody serpent or divine goddess isn't just sensible, it's poetic survival. I once tried creating a new myth myself, involving a jealous moon who pulls the oceans close because the sun keeps flirting with the earth. The story was well received until I accidentally animated it using sock puppets, and the whole thing descended into chaos involving a toaster. But I digress. The point is the tides have always moved us, not just physically, but emotionally and spiritually. They are metaphors for longing, change, return. They remind us that time flows in cycles, that forces unseen shape our world, and that sometimes the sea just wants to keep the shiny things we throw at it. Next, we'll explore how tides interact with modern climate. In the great theatre of Earth's natural systems, tides have long been among the most consistent performers, reliable, steady, comforting in their routine. But as with any long-running production, there's a new plot twist, and it's one that threatens to flood the stage. Let's talk about sea level rise. It's no secret that our climate is changing. Glaciers are melting, ocean temperatures are climbing, and as a result, global sea levels have risen by about 20 centimetres since the start of the 20th century. That may not sound like much, roughly the height of a particularly stout sandwich, but in coastal terms, it's rather a lot. Tides, of course, continue to do what tides do, rising, falling, ebbing and flowing, but now they're doing it from a higher baseline. Imagine a bathtub where someone keeps pouring in more water. The tide still comes in and out, but now it sloshes over the edge more often, soaking your bath mat and threatening the downstairs neighbours. In places like Venice, Miami, Jakarta and the Maldives, this is not metaphor, it's Tuesday. High tides are now overlapping with storm surges and heavy rains, leading to what scientists call nuisance flooding, and locals call, well, that's ruined the sofa again. The trouble is that tide systems were never meant to work with shifting baselines. Entire ecosystems, salt marshes, mangroves, intertidal flats, depend on the delicate timing and height of tides. When sea levels rise, these zones either migrate inland if they can, or vanish if they can't. It's a bit like moving the piano mid-performance. Things go flat rather quickly. Urban infrastructure is also at risk. Sewers designed with 20th century sea levels in mind are now backing up. Roads are eroding, basements are becoming impromptu aquariums, and tide charts that once predicted safe harbours are now being rewritten with disclaimers and very tiny footnotes. Some places are adapting. Cities are installing tidal gates, elevating buildings, restoring wetlands and rethinking coastal planning. But adaptation requires money, political will, and the ability to look more than one election cycle ahead. It also requires an understanding of tides not just as background scenery, but as active, powerful agents in our relationship with the coast. I once tried to design a self-adjusting beach chair that would rise and fall with the tide, keeping the sitter perpetually dry. It worked well until a minor miscalculation launched my Uncle Herbert into a sandwich kiosk. Still, the principle remains. As sea levels rise, so too must our awareness of how the tides will respond. Because they will respond. Not in a dramatic flourish, but in the slow, insistent language of erosion and overflow. Some scientists are now studying how tidal amplification may occur with climate change, how higher sea levels might actually make tidal ranges more extreme in certain regions. Others are tracking how gravitational interactions might subtly shift as mass redistributes around the globe. It's all very complex, a bit alarming, and occasionally discussed over very strong coffee. So the next time you visit the coast and see the tide reaching just a little higher than you remember, don't assume it's nostalgia playing tricks. The ocean is rising. The tides are still keeping time, but the clock tower is leaning. Next, we'll look at how tides may influence renewable energy, because when the sea pulls, there's power in that motion. Quite literally. Tidal power. When the sea does the heavy lifting. If there's one thing we've established by now, it's that the ocean is strong. Not just carry your picnic basket strong, but rearrange your entire harbour strong. So it's perhaps no surprise that we've started harnessing this immense energy for our own benefit, using the pull of the moon and the push of the sea to generate electricity. Enter tidal power. Now the basic idea is delightfully simple. Water moves. We catch that movement. The movement turns something. That something spins a generator. Voila. Watts, volts, and the smug satisfaction of renewable energy. But the devil, as always, is in the soggy details. There are three main types of tidal power systems. First, there's the tidal barrage. This is essentially a dam built across a bay or estuary. As the tide rises, water flows into a reservoir. When the tide recedes, the water is released through turbines, which spin and generate power. It's a bit like building a giant plug hole that also makes toast. It doesn't, that would be dangerous, but you see what I mean. The most famous of these is the Reims Tidal Power Station in Brittany, France. Completed in 1966, it was the first of its kind and is still operational today. It generates around 540 gigawatt hours per year, which is enough to keep quite a few kettles on the boil. Next, there are tidal stream generators. These look a bit like underwater wind turbines, placed in areas where strong tidal currents pass through narrow channels. They're less intrusive than barrages and work rather elegantly. Imagine the sea gently spinning a series of submerged pinwheels. These systems are being tested and deployed around the UK, particularly in Scotland, where tidal flows between the islands are famously vigorous, and where engineers are remarkably tolerant of damp socks. Lastly, we have dynamic tidal power. This is more theoretical, involving long dams jutting out from coastlines to exploit tidal phase differences. It's like building a horizontal skyscraper into the sea and waiting for the ocean to argue with itself. While tidal power holds great promise, it's not without challenges. Construction is expensive, marine ecosystems can be disrupted, and saltwater has a habit of corroding anything with aspirations of lasting more than a fortnight. Still, the allure of predictable clean energy from the moon's pull is hard to resist. Unlike solar or wind, tidal energy is gloriously dependable. We know to the minute when the tide will turn even a century from now. That reliability makes it a darling of grid planners and a source of endless delight for engineers with waterproof notebooks. I once tried building a small-scale tidal generator in my garden pond using an egg whisk and bicycle parts. The local frogs were unimpressed, though one did use the device as a diving board. But in seriousness, tidal energy represents a beautiful intersection of ancient rhythms and modern needs. It reminds us that the very forces which once inspired myth and guided ships can now power our kettles and light our homes. Next, we'll explore the emotional tides, the psychology of watching the sea, and why so many of us feel drawn to its rhythmic sigh. Some people visit the coast for a bit of sun. Others seek out the salt air for its supposed curative properties, or to chase seagulls with sandwiches. But ask around long enough, and you'll find that many people are drawn to the sea for something more mysterious. An emotional pull, a longing, a sense of vastness and return. We speak of being called by the ocean, of finding ourselves by the waves. And this isn't just poetic fluff from overly caffeinated writers, though we do contribute. There's something in the rhythm of tides that echoes the quieter rhythms of human experience. Psychologists have long noted that natural rhythms, day and night, the seasons, the phases of the moon, affect our mental states. It's no surprise, then, that the tide, with its hypnotic rise and fall, can have a calming effect. It's the original white noise machine. It's a lullaby that predates lullabies. Some researchers suggest that watching the sea can induce a mild meditative state. The constancy of movement, the shifting textures, the horizon holding steady. It's like therapy with a soundtrack and better air quality. This, they believe, activates the brain's default mode network, which is associated with introspection, creativity, and a general sense of aha. The sea also offers scale. You stand beside it and feel, quite rightly, small, but not insignificant, just correctly sized. In a world of relentless screens, pings, and things that urgently require your attention, most of them involving expired passwords, the ocean says, none of that matters right now, watch this wave instead. There's also the symbolism. The tide leaves and returns, a pattern we all know too well from people, emotions, seasons of life. The sea becomes a mirror, not in the literal sense, unless it's very still and you're having a good hair day, but metaphorically. We project our inner states onto its vast surface. Many people report feeling emotionally cleansed after time by the water. Whether it's the negative ions in the air or simply the chance to sit with one's thoughts without interruption, the coast has long been a favoured retreat for the weary, the heartbroken and the overbooked. It's no accident that so many artists, philosophers and romantics have had seaside epiphanies. Virginia Woolf, who grew up in a coastal town, wrote of the sea as a presence that seemed to flow through her. Carl Jung associated water with the unconscious mind. a repository of feelings, dreams, and repressed memories, all sloshing about just beneath awareness. Even my own great-aunt Petunia, who was a woman of few words and many cardigans, maintained that the only proper place to cry was on a bench facing the sea. "No one minds there," she once said, handing me a thermos and a large napkin. "I too have found solace in tide watching." There's something deeply reassuring in seeing the sea come back again and again. It reminds us that no matter how far things drift, our plans, our hopes, our sandwich crusts, they might yet return. So if you find yourself standing at the edge of the world staring out at the surf, don't feel silly. You are part of an ancient conversation, one that speaks in sighs and foam and pauses just long enough for you to catch your breath. Next, we'll begin tying things together as we approach the end of our tidal journey, looking at how science, myth, and motion meet at the water's edge. Meeting at the shore, where science, myth, and memory collide. As we near the end of this lunar-lit ramble, it seems only right to pause and reflect on what the shore really is. A place of convergence. It's where land meets sea, yes, but also where knowledge meets mystery, data meets poetry, and science meets the kind of dreamy bewilderment that can't quite be plotted on a graph. Tides themselves are the ultimate symbol of this convergence. Governed by gravity and orbital mechanics, they are precision in motion, predictable, measurable, and delightfully Newtonian. Yet they are also deeply personal, inspiring myths, shaping memories, and leaving damp patches in precisely the wrong part of your trousers. When we look at the sea's rhythm, we are seeing a system that is both entirely outside ourselves and intimately familiar. Its constancy comforts us, its vastness humbles us, and its relentless pull, both literal and metaphorical, makes poets of even the most scientifically minded. One might argue that tides have always been interdisciplinary. You can't fully understand them with equations alone, nor fully feel them through story alone. You need both. That's why you'll find tide tables in nautical logbooks and gods of the sea carved into ancient altars. It's why schoolchildren can recite phases of the moon, while their grandparents still mutter about spring tides and full moons making people act funny. Even the language we use around tides is telling. We go with the flow. We are swept away, we are adrift or anchored. These phrases aren't just metaphor, they reflect a human intuition that we too are moved by forces greater than ourselves. In my own life, I've come to think of the shoreline as a sort of chalkboard, a place where the universe scrawls equations in foam and sand. They are erased and rewritten twice daily, always changing, yet always recognisable. I once attempted to write E=mc² in driftwood letters during a retreat in Pembrokeshire, but a particularly feisty puffin took issue with the placement of the equals sign and rearranged it into something closer to B=T². Arguably more useful. There is wisdom in that puffin's edit, though. Tides aren't just about motion, they're about moments. Standing at the edge of the world, ankle-deep in moving water, you're given the rare gift of feeling the planet do something. Not just spin or orbit or exist abstractly, but move you, physically, psychologically, sometimes sandwichily. As we tie together threads from myth and measurement, emotion and observation, we begin to see the shoreline not as a boundary, but as a bridge, a meeting place, a laboratory where you don't need a lab coat, just patience, curiosity, and perhaps a waterproof hat. So the next time you find yourself by the sea, whether in person or in thought, let yourself be drawn. Watch the tide. Time it, if you like. Or don't. Let it pass over your toes and your troubles. Let it pull stories out of you that you didn't know were there. Next, in our penultimate chapter, we'll consider what the future holds for our understanding of tides and how the next generation might come to know and love them, as scientists, storytellers, and soggy wanderers alike. The tides have always whispered to those willing to listen, and though their rhythm is ancient, their relevance is anything but outdated. As we stand on the cusp of climate shifts, technological leaps, and evolving curiosities, the question arises, what does the future of tides look like? To begin with, science is not done with them, not by a long chalk, and I do have an excellent collection of chalks. Tidal modelling is becoming more advanced by the day, using satellites, AI, and mind-boggling equations that once lived only in the notebooks of eccentrics with wild hair and dubious tea preferences. Now these tools help us understand not only where water will be, but when, why, and how high it will slap the promenade. One exciting area is in tidal forecasting for extreme events. While ordinary tides are predictable, their interactions with storm surges, sea level rise, and altered wind patterns are not. The next generation of models may help us protect cities, design better coastal infrastructure, and decide precisely when it's safe to walk your spaniel. There's also an emerging field of tide-inspired engineering. Architects and designers are looking to the predictability of tides for solutions: floating houses, amphibious parks, and tidal-powered desalination systems. And in schools, students are learning to code tidal data, visualize wave cycles, and understand planetary mechanics by tracking moon phases with their mobile phones. A bit more high-tech than my lunar calendar made of biscuit tins. Culturally, tides are poised for a renaissance. As more people rediscover natural cycles in their quest for mindfulness, sustainability, or just a break from inboxes, the sea offers a rhythm that speaks to something deeply human. I wouldn't be surprised if tide-watching apps became the next big trend. Tide Talk, perhaps, featuring moody ocean videos and seaweed-based life advice. And as we face the complex pressures of climate change, the tide may well become a symbol not only of change, but of hope. Because even as the planet warms, the tide keeps coming back. Even as the coastline shifts, the moon still tugs. That constancy is a reminder that not all cycles are broken, and that some can still be relied upon. For children growing up in this new tidal era, the ocean will not be a distant thing. It will be present, rising at their doorsteps, featured in their textbooks, influencing their holidays, but it will also be beautiful. It will inspire songs, spark research, invite awe, and it will remind them that science isn't just something you do in a lab, it's something you live every time you paddle at the shore. I've taken great comfort over the years in returning to the sea. With each tide I feel a little less scattered, a little more aligned. It's humbling to think that the future of tides will be written not just by professors and programmers, but by school children with sketchbooks, storytellers with microphones, and perhaps even you. Next, in our final part, we'll bring it all home, literally and figuratively, with a cup of tea, a view of the sea, and a few final thoughts from your devoted narrator. And here we are. If you've made it this far, congratulations. You've followed the moon's pull through a winding path of gravity, water, myth, science, sandwiches, and the occasional sock puppet. Now, as our journey draws to a close, it's only right that we return to where it all began, with a cup of tea, a window looking out toward the coast, and a world that keeps moving, even when we're still. Tides are more than just movements of the sea. They're metaphors, mechanics, mood setters, and timekeepers. They remind us that we are part of something larger, something ancient and ongoing. No matter how complicated life gets, the ocean still pulls itself up the shore and gently recedes again, as if to say, there, everything moves, everything returns. We've learned how gravity from the moon and the sun choreographs this dance, how the shape of continents, bays and seafloors subtly alter the rhythm. We've explored resonant bays, haunted coastlines, myths of sea gods and moon dwellers, and the science that stitches it all together. But perhaps what matters most is how the tide makes you feel. Whether you're knee-deep in equations or knee-deep in seawater, the experience of standing beside a living, breathing ocean remains one of the most grounding and uplifting things a person can do. There's something inherently British about this, I think. A quiet reverence for large forces, a willingness to have your picnic interrupted by damp breezes, an acceptance that even the best-laid sandwiches may one day be claimed by a passing gull. We love our coastlines, we measure our lives by them, and we always pack a thermos. I have been honoured to be your guide. Once a lecturer in planetary physics at a mid-tier university, with a leaky roof and a vending machine that only served digestives, I have spent decades pondering the great questions. Why does the sea rise? How do we know? And where, oh where, did I put my trousers? If I've managed to help you sleep or smile or simply stare out your window with a bit more wonder, then I consider this expedition a success. As we wrap up this first episode of Tea and Gravity, I leave you with this. The sea doesn't stop. Neither should your curiosity. Let the tides guide your thoughts, your questions, and perhaps your next adventure. And as always, mind the damp, bring a biscuit, and never ever try to outstare a puffin. Until next time, sleep well, dream deeply, and may your teacup never be empty. And so, dear listener, As the last of the teacups cools and Pig begins to snore most contentedly on the windowsill, we come to the end of tonight's tale. If you've enjoyed this little ramble through the improbable and the quietly profound, do be a dear and like the episode and subscribe to the channel. It helps keep the tea flowing, the lights low, and the cats, both remembered and yet to be, well fed and purring. And don't forget, you're warmly invited to join our free Substack. It's where you'll hear about each new episode as it arrives, and where our growing circle of sleepy science enthusiasts gathers to swap thoughts, dream up topics, and gently bicker about whether Pluto should bring a casserole to the next planetary reunion. Now, one last thing. Tonight's story has been for entertainment purposes only. It is not, strictly speaking, fact. Nor is it entirely fiction. Rather, it exists in that peculiar quantum superposition of the two until observed, preferably over a cup of something warm. Sleep well, and until next time, may your teacup never be empty.